So when the two oceanic plates came together, we got that very deep trench. We also had a subduction zone, and we have the islands, the Mariana Islands, because of that. So the Marianas Trench is the deepest. They said it was 36,000 feet deep. Okay. Does anybody remember how many feet are in a mile? 5,280. Okay, and so we're talking relatively about 7 miles under the ocean is the deepest place. That's a very deep trench. Unfortunately, we are finding plastic bags and debris at the bottom of this trench, kind of an influence of us living here. In terms of the fact that an oceanic plate is going down, it melts, and we have volcanoes. Around the area where the highest mountain range, the Mount Everest, we have no volcanoes, but the two continental plates are pushing up to create the highest peak in the world. Now, if we put the highest peak in the Mariana Trench, you'd still have a mile of water before you got to the top, and so we are much deeper in the ocean than we are taller on top of the land. Now remember that we talked about rocks and how they can change, the rock cycle. A lot of times the rock cycle actually happens at subduction zones where sedimentary igneous rock can be pushed under the crust where there's heat and pressure, and this is where a lot of the metamorphosis happens. And as you raise mountains, you can have the erosion take place to create sedimentary rock. And if you push everything far enough down, the metamorphic rock, the sedimentary rock, and the igneous rock will melt and then reform igneous rock when when it comes up to the surface. And so here is where the rock cycle actually lives and can be seen. Now I told you that faults move large plates that are around, and the North American continent, the actual U.S., sits on two plates. Now the majority of the U.S. is on the North American plate, which is moving in a direction that is going down to the south and the east. So it goes down southeast. And the Pacific plate is going up to the north and west, heading towards the northwest. Now, when my family moved from Virginia to California, everybody was worried and talked about, oh no, California is going to fall into the ocean. Well, not really, because that's not the way it's actually moving. There are a lot of earthquakes, and so the cities and the land is actually moving this direction in most of California and moving in this direction for the rest of the United States. What is actually happening and what could happen is Los Angeles won't fall into the sea, but actually Los Angeles is moving closer to San Francisco. And the San Andreas Fault actually goes directly through San Francisco and out the bay of San Francisco. I was watching a news show, and in San Francisco, if you earn, I believe it's like $110,000 a year, you're at the poverty line. You're in San Francisco because of how expensive it is to live there. And so, yeah, that seems to be a lot of money, right? And in most of the United States, $110,000 sets you up pretty well every year. But when you're paying $3,000 to $4,000 for a one-bedroom apartment in San Francisco, money doesn't go so far. Lots and lots of very expensive real estate that sits just on top of the San Andreas Fault. And so they've had earthquakes that have destroyed the city, but people still want to live there. And so the movement of this fault is a strike-slip fault. So neither one of the plates are moving up or down. They're moving past each other. We call that parallel movement. And so there's not going to be mountain building at that particular fault It's going to slide past each other. You wouldn't even know. Now, right here, you can see where the fault is. Right here, way down here, it's flat ground. You could walk over that fault and not even know it. You could actually build a house on top of the fault and not know it. And for most of your life, it might be okay. But well, it was last week or the week before, there was an earthquake, 7.1 magnitude. One of the interesting pictures that you can find online is the satellite picture before and after. Before, it was nice, smooth desert. After, you can actually see the crack where the fault actually is. For a little time, you'll be able to see that, but dirt will fall in, and it will cover it, and then you can't see it again. And so it's there, but sometimes you don't actually see that it's there. Now, we told you that the plates move, okay? And we really believe that happens because of a lot of pieces of evidence. And if you take a look, one piece of evidence is called a hot spot. It's a place where magma under the earth is very, very liquid. And it comes up over time and it will create a volcano, and that volcano under the ocean may create an island. But what happens as the crust is moving above that hot spot, I'll create an island every so often, and then the crust moves far enough. But the magma is always coming up from one central area, and so in the Pacific particularly, you see what are called island chains. Hawaii is a wonderful example. And so the hot spot in Hawaii, all of these islands were over that hot spot at some point in time. Currently, the big island of Hawaii has an active volcano that is always erupting, and it's a fairly gentle eruption. But if you take a look at this island right here, what you see is a much larger island than all of the rest. What does that say about the plate movement that's happened really recently? It's slowed down. And so the plate movement isn't constant rate. It's not going down the interstate at the same speed entirely. It moves and then it stops. And it's kind of jerky. Move and stop, move and stop. Sometimes it stops for a longer time. Sometimes it moves at a faster rate. And so we look over at averages, but what this tells us is that the plate is about ready to move. It needs to move. It's been sitting on one spot for a long time, longer than the others, and so it's relatively, it should be at a place where it should move. Other things, what's called paleomagnetism at the divergent zones, when it opens up, okay, at the opening up, we have volcanic eruptions and magma comes up, and so there's a layer on this side and a layer on that side that came together at the same time. The green is what's new. And then if I look at this layer, this is an eruption, and this one on this side is an eruption. Those two were related. And so the reds were together at one point in time, and then it moved, and then you had the second eruption, and then it's moved, and you've had the third, and it'll move again. But what happens is the red, the north is here. This other color, the north is here. And in the green, the north is here. The reversal of the magnetic fields indicates that, yes, the plates are moving, and in this case, away from each other. Earthquakes, you have to have movement of big plates to have earthquakes, so that actually supports the idea that the plates are moving. And the ages of the sediments, what we find on the bottom of the ocean are very young compared to the crust that's part of the continent. So we're laying down the erosion, and at the bottom of the oceans, all of that very young erosion is right at the top. What is the driving force, or what moves the plate tectonics? You saw the video of the convection current. that will move the plates. That is one of the major theories of the driving force, what actually powers everything moving. The other idea is what's called the slab push-pull. And what happens is, as these plates come down, okay, to the edge, and I'll get to one over here. So that's at the middle where the heat's rising. But over here at the edge, that plate dives down into the center of the Earth. As the edge goes deeper and deeper, it's getting pulled by the gravity, and gravity is pulling the edge of that plate, which also pulls the rest of the crust. And so the fact that part of it is falling and the gravity it's pulling, and the fact that there are places in which the heat is rising and creating convection currents, those are the two mechanisms that work together that are the best ideas about why we have the movement of the plates. Now, it's hard to test this theory. It's hard to get evidence because it all is happening under the crust, which is hard to observe. But we know on average the plates are moving about 3 centimeters per year. And so if you moved for, let's say, 100 years, you would move 300 centimeters, which is the same as saying 3 meters, because there are 100 centimeters in a meter. And so we can measure that now. We can take satellites and look at the coast of the west coast of Europe, the east coast of America, and we can actually measure how far the distance is away from those. Now, this is my favorite theory about why plates move.